Hello everyone. In this video, I'm going to present SD4Match, which explores prompt tuning for Stable Diffusion on the task of semantic matching. Recent research by Dift and STDino has shown that the intermediate output of the UNet of Stable Diffusion at a specific time step can act as the feature map for semantic matching. As illustrated, an image is first encoded to its latent representation by the diffusion model's VAE encoder. Then, using DDIM inversion, it is inverted to a specific time step t. This inverted latent representation, along with the time step and prompt, are passed through the diffusion model's UNet. The intermediate layer's output is then used as the feature map for semantic matching. In this work, we first review that the performance of Stable Diffusion on semantic matching can be easily enhanced by prompt tuning. We then propose a conditional prompting module which generates prompt for each individual image pair to further boost the matching accuracy between them. This is the illustration of the general pipeline. The feature maps FAT and FBT are extracted from images as described before, but using the trainable prompt instead of the handcrafted prompt as in Dift. The supervision to the prompt tuning is the cross-entropy loss between predicted and ground truth matching probabilities of the query point. Under this pipeline, we investigate three prompt tuning designs. The first one is to learn one universal prompt for everything. We denote this design as SD4Match single. The second design is inspired by Dift, which uses the category of matching object as the prompt. Therefore, we learn one prompt for each object category and denote it as SD4Match class. The third one is our proposed conditional prompting module, which takes two images and generates a prompt specifically for semantic matching between this image pair. We denote this design as SD4Match CPM, and we'll talk about it in details. Our CPM first uses DynoV2 to extract global and local features of two images. Next, we concatenate the local features of both images, using a single linear layer to mix them along the channel dimension, and a second linear layer to project the features along the patch dimension. Adaptive max pooling is then applied to ensure the number of patches does not exceed the diffusion model's limit. This feature is combined with learnable weights, positional embeddings, and a global prompt to produce the final prompt. The trainable part includes two linear layers, the learnable weights, positional embeddings, and the global prompt. Unlike other prompt tuning methods, our CPM uses local features instead of widely used global one, as image matching focusing on local details, and includes a linear projection along the patch dimension to facilitate information exchange between patches. The importance of these components will be highlighted in the ablation study. We evaluate three designs of SD4Match on SP71K dataset. As demonstrated, we achieve the best result among all object categories. Specifically, SD4Match CPM achieves the comparable result to SD4Match class, but does not need to know the category of the matching object in advance. We also test the generalizability by training it on the PF-Pascal dataset and evaluate it on PF-Pascal, PF-Willow, and SP71K datasets. We achieve the best result among methods tuned on the PF-Pascal dataset, but observe a performance deterioration on the SP71K dataset compared with zero-shot methods. We attribute this to the fact that the PF-Pascal is a relatively small dataset, so tuning the model on it may cause a certain degree of overfit. If we look at SD4Match tuned on the larger SP71K dataset, we surpass all zero-shot methods. We conducted two ablation studies. On the left side is the ablation study on the design of CPM, and it shows the advantage of using local features, conditioning on image pairs, and patch-wise linear projection. On the right side is the plot of accuracy against time step. As demonstrated, SD4Match improved over baseline Dift across a wide range of time steps instead of at some specific ones. For more experiment results and method details, please visit our project webpage and check out our paper. Thank you for your attention.